Okay, after my performance Friday and my pitiful explanation of a series approximation to a solution of a differential equation, I thought I would do another short video. Well, I hope it's short. And let's look at this example. Now, this is an example of a problem I put on an exam before. And if you notice, this function, this differential equation, is undefined at x equals -1. Well, x equals -1 is called a singular point. Now, for any other value of x, this differential equation is defined and makes sense. The other day, Friday, I tried to work a problem where there was an x squared here, I believe, in this lead term. So that function was not analytic at 0. Analytic just means it's defined. Well, that problem was not defined at 0, and I tried to do a series expansion centered at 0. I tried to do a Maclaurin series expansion, and it just doesn't make sense. So it was a bad selection of problems on my part. And I apologize, Friday was not a good day. Let's see if we can do a little better on this one. Now, as I stated on the last handout, the handout I posted yesterday, this looks really complicated, but it isn't. It is not. So let's go. Let's run through this real quick. We're going to do a Maclaurin series. We're going to do a series approximation of the solution to this, and we're going to center in at 0. It would not make sense to do a Taylor series expansion around -1 because it's not defined at -1. But for any other x value, this function, this differential equation is what we call analytic. It makes sense. So we're going to do an expansion around x sub 0. So we're assuming that the answer looks like this series. N equals 0 to infinity, c sub n, x to the power of n. And just remember, this would be c0 plus c1x, c sub 2 x squared, on and on and on. Then the first derivative, we just differentiate this, but when we differentiate it, we lose the first term. So the first derivative is going to begin at n equals 1 to infinity. And then you just differentiate this expression. In general, this is n c sub n x to the power n minus 1. And then if we differentiate again, we'll lose another term because, see, the first derivative, this is 0. The first derivative would be just c sub 1. Then the second derivative, that term goes away. So with respect to the original one, we have now lost 2 terms. So the second derivative series will begin at n equals 2 to infinity. And then just using the power rule, we'll have n times n minus 1, c sub n, x to the power of n minus 2. So what are we doing? We're just using the power rule of differentiation on a polynomial. This is just an infinite polynomial. At the heart of what we're doing is just differentiating a polynomial. And that's about the easiest thing you can do in calculus. Now, we just want to plug the pieces in. I'm going to plug that into the second derivative, and I'm going to plug this into y. So then we'll get x plus 1 sum n equals 2 to infinity n times n minus 1 c sub n x to the power n minus 2 minus then the sum n equals 0 to infinity c sub n x to the power of n, and all of that equals 0. Remember, when we get finished with this, on the left, we're just going to have a very wild-looking expression, but it's just a polynomial. Okay, now what I want to do is the distributive property and multiply this series times each term. And that's going to give me an x times the sum. And okay, are we clear on what I did? I just took this times 1, which is this term, and I took this series, this series, a summation expression times x. Now, when I multiply through by x and add the exponents, this exponent becomes n minus 1, because what we have is n minus 2 plus 1. So distributing that through, we're going to get this. Okay, now this looks off the chain, but it isn't difficult. It isn't difficult. Now, we're going to do two things. And as I mentioned in class Friday, if you wanted to, you could rewrite these three terms so that the exponent was always n minus 2. Or you could change all of them to n minus 1. Or you could change all of them to n. It doesn't matter. But if you're not careful, you're going to end, in a minute, you're going to end up with a summation, n equals a negative number. And as I said Friday, that really upset people, because nowhere in the discussion of infinite series in Calc 2 did you ever have a negative number here. Now I'm going to come back to that. Regardless of which one of these you pick and you change the other two to that exponent, you're going to end up with the same thing. So what I do, without loss of generality, I always change everything to n. I always change everything to n. All the exponents to the power n. So let's take them from left to right. I need to do kind of a transformation here. For this exponent to become n instead of n minus 1, I need to replace n with n plus 1 everywhere. Everywhere you see an n, I'm going to put n plus 1. And then see, I'll have n plus 1 minus 1 gives me the exponent n. So let's do that. It's not a big deal. So I'll have n plus 1 equals 2, the sum. Now I'm going to have an n plus 1. And then I'll have n plus 1 minus 1, which is just an n. This would be c sub n plus 1, and then x to the power n. Okay, let's go to the next one. For this one to become, for this exponent of x to become n, we need to replace n with n plus 2. So everywhere I have an n, I'm going to plug in n plus 2. Well, let's just do it. We'll get n plus 2 equals 2. to the power to the upper limit of infinity, the upper index of infinity. Now I'm going to have an n plus 2 times then an n plus 2 minus 1, so that gives me an n plus 1. This becomes c subscript n plus 2 x to the n. And then this one is unchanged. Okay, but like I said Friday, it would have been perfectly okay if we changed all the exponents to n minus 2 or n minus 1. Or for that matter, we could have changed them all to n plus 7 and it would still work out just fine. And again, without loss of generality, I just change them all to n. Now let's rewrite this. We have n plus 1 equals 2. And that means if we subtract 1 from each side of this little equation, I get the sum of n equals 1 to infinity, n times n plus 1, c and the subscript is n plus 1, x to the n. And this one's going to be the sum, n equals 0 to infinity, n plus 1 times n plus 2, c subscript is n plus 2, x to the n, and then this one so far has been along for the ride. Okay, that's half of what we've got to do. Okay, so I'm going to copy this. I'm going to copy this last statement to the top of another page, and we'll pick up right there. Okay, so here's what we've got from the previous page, rewritten at the top. Now, what I want to do, I want all these subscripts at the bottom to begin at the same thing. Well, see, I cannot make this one begin at 0 easily, but I can make these begin at 1, n equals 1, simply by letting n equals 0 plug in, and then everything left in this series will begin with 1. So let's do that. I'm simply going to pull a term out of this, and I'm going to pull a term out of this one. And let's see what happens. This one is unchanged. Now, in this middle one, I'm going to let n equal 0. So 0 plus 1 is 1. That's 2. So 1 times 2 is 2. So I'll get a 2. Now, if n is 0, this is going to be c sub 2. And if n is 0, that's x to the 0, which is 1. And then all the other terms would begin with n equals 1. Now we're going to do the same thing with this one, but now remember you've got a minus out front. So if I let n equal 0, all I get is c sub 0. And then I'll have minus, and all the rest of them begin at n equals 1. Okay, now I'm going to collect these two by themselves. So that's going to give me 2c sub 2 minus c sub 0. Now, notice what we've got here. All the summations begin at n equals 1, and all the variables of x, all the exponents of x are n. So we can do this. You didn't see this in count 2. So see, now that can be rewritten that way. Now here's what we've got. On the left, this is just a obscene polynomial, just awesome looking. And on the right we have 0, but 0 is a polynomial. And that means the coefficients of x on the left have to equal the coefficients of x on the right. Well, on the left we have this constant term. So it must be the case that 2c sub 2 minus c sub 0 is 0. And now, when something like this happens, you pick on the biggest one. You want to solve for that one. So that means then that c sub 2 is 1/2 c sub 0. Cool. Nice. Now these are all the coefficients of x beginning with n equal 1, beginning with x to the first power, and then x to the second power. They have to, one by one, equal 0. So I'm going to set this equal to 0. Now what you do, and you do this every time, you pick the biggest expression, c sub n plus 2 in this case. So you're going to set this equal to 0, and you're going to solve for c sub n plus 2. When you do, you get this. Now you're going to move c sub n over to the right side. You're going to move this over. It becomes minus. And then you want to divide by the coefficient of c sub n plus 2. Now, this generates coefficients of that original polynomial, and this is valid for n greater than or equal to 1. Well, where did that come from? Okay, now look, what you put right here is this lower subscript in all the sums, once we have rewritten it, is n equals 1. So this begins as n equals 1. See, this is n equals 1 here. If this had been n equals 5, then this expression would have been valid for n greater than or equal to 5. Let's just plug some numbers in. Let's begin at n equals 1. So we'll let n equal 1. Now when you plug 1 in everywhere. So you'll get c3. So this is going to be the coefficient of x cubed. c3 is going to be c1. Now 1 plus 1 is 2. 2 times 1 is 2. So this is minus 2 c sub 2. And then downstairs you have 1 and 1 is 2. 2 plus 1 is 3. So this is a 6. Right? 1 plus 1 is 2. 1 plus 2 is 3. 2 times 3 is 6. Well, that looks pretty good. But remember, C2 is 1/2 c sub 0. So I'm going to write this as 1/6 C1 minus 1/3 c sub 2. But that's 1/6 c sub 1 minus, now I want to put 1/2 c sub 0. So I'm going to get 1/6 c sub 0. So that's what the coefficient of x cubed is. Now on the exam, I'm not going to ask you to find all of the coefficients. I'm going to what I typically do is have you find the first 4 non-zero coefficients. Well, see this, you can crank out as many coefficients as you wish with this one. So if this was a test problem, and it was a test problem, we would let n equal 2 then, so 2 plus 2 is 4, so this is the coefficient C4. This is the coefficient of x squared. And we're going to come back up to our recipe, and everywhere we have an n, we're going to put a 2. So this is going to be c sub 2 minus, this is going to be 2 times 3, so a 6 c sub 3. And then downstairs we'll get 3 times 4 is 12. So this is 1/12 c sub 2 minus 1/2 c sub 3. But now look at this. Can you see what's going to happen? Right here where I've got that c sub 2, I'm going to put in 1/2 c sub 0. when I do that, when I put in 1/2 c sub 0, that's going to give me a 1 over 24 c sub 0. Now I've got a 1/2 c sub 3, and for c sub 3, I'm going to plug this in. Ooh, it looks like a mess. So I'll get 1/2 times 1/6 c sub 1 minus 1/6 c sub 0. Oh my goodness. And then c sub 4 is going to be a 24th c sub 0 minus a 12th c1, and then plus 1/12 c sub 0. Okay, now 1/12 is equal to 2 over 24. 2 over 24 plus 1 over 24 is 3 over 24. So that's going to be a 1/8 c sub 0 minus a 1/12 c sub 1. And we're going to stop right there. Now I'm going to start a new page. I'm going to write down all the information, and then we're going to write down the answer, because we're finished. And in fact, on the exam, the main thing I look for is to see if you can get that right. If this is correct, then with sufficient time, you could just crank out the coefficients of the original polynomial. Okay, so see you in just a second. Okay, well, this is what we've got. This is what we've got. Now remember, we began this whole thing, this whole discussion, by assuming the solution looks like this. Now, all I'm going to do is plug in what I know. I've got a c sub 0, and you see everything up here, C2, C3, C4, is written in terms of c sub 0s and c sub 1s. So I'm going to leave that c sub 0. I'm going to leave this one c1 of x. And now, where I've got c sub 2, I'm going to put a 1/2 c sub 0, x squared. Where I've got the coefficient of x cubed, c sub 3, I'm going to put in 1/6 c1 minus 1/6 c sub 0. The coefficient of x4, of x to the 4th, c sub 4, is going to be 1/8 c sub 0 minus 1/12 c sub 1. And they can just keep going. And believe it or not, that is your answer. Now, let's discuss this. Suppose we had the original problem . There's our original problem, but suppose we were given this information. Okay, suppose it's an initial value problem. That means we're going to get numbers here. Well, let's see what happens. If I come up to the original expression right here, if I come up to right there and plug 0 in for x, that's going to give me c sub 0 is 0, isn't it? So back up here in this answer, everywhere I have a c sub 0, I'm going to get a 0. Now, the first derivative, if we differentiate this thing, we get a c1, right? Let me just write that down. Y prime is going to be a c1 plus a 2c sub 2x and 3c sub 3 x squared, on and on. Now if you plug 0 into this, y prime of 0 gives me 1 is going to imply that c1 is equal to 1. So it turns out if you're given an initial value problem, you can come right back up here and then state, okay, given these initial conditions, our answer is going to be, remember, c sub 0 is 0 and c1 is 1, so we'll get an x. That term is now 0. That is 0, so we'll get plus 1/6 x cubed. And then that's 0, and then we'll have a minus 112 x to the 4th. On and on and on. But now, on the exam, I'm not going to give you an initial value problem, because that would require you to do just that much more. I'm going to have you stop right there. And remember, in addition, what I am looking for, I am looking for this right here. That's what I'm looking for. Because if you get this right, then you will eventually get this correct. If you get this incorrect, then this is not even going to happen, is it? So the important thing is this. So I hope that helps a little bit, and I hope this will aid you as a little supplement to what we do on Monday. Thanks.